Okay, Physics 15. So today we're going to be going over Chapter 16. That's right, you heard it, Chapter 16. Because this is the last week. We have final exams next week. So we're just going to do Chapter 16. We're not going to do the whole thing. We're only going to go up to page 336. We're going to cover the most important aspects. This is important to know. You got to know this. I skipped the last chapter. You know, you got to draw the line somewhere so the semester ends. We had a good semester. We covered a lot. We covered a lot of material this semester, really. So we did good. We did good, right? We did really good. So chapter 16, light and waves. Let me adjust the camera. I hope everyone is staying safe. Let me adjust the camera, and we're gonna get into this, okay? We're gonna get into this, so let's do it. All right, bear with me. We'll just do it this way, rather than turning off. We'll just keep doing everything. All right. All right. So yeah. So I'll be sending out. I'll be putting an announcement on Canvas. Also sending out an email as to the details for the final and all such, okay? So here we are. And chapter 16 in the book, right? So here's the book, Light, Waves, and Color, and let's move along. We're gonna go here, okay. So what do light, we all know what light is. Light is coming through this window right now, right? It's still daylight outside. And, radio waves. Well, we all know what radio waves are. We all have radios. We have radios in our cars, right? You just turn a radio on and it picks up the radio station. So radio stations are broadcasting somewhere. They broadcast over radio waves. TVs broadcast over this too. When I was young, everyone had TV antennas on their house because that's the way all TV went. They had a TV station, it broadcast over electromagnetic waves, and people had antennas. Now, of course, everything is cable, right? It's changed. So, microwaves. Well, I know you've all heard of a microwave oven. Microwaves were here first. Microwave ovens are named after microwaves. What they found that these waves, microwaves, they heated up water quite well. Water absorbed that energy. It absorbed that energy, so they made ovens out of it. It's just a transmitter that just transmits at one specific frequency, one specific wavelength. We'll talk about that. And it heats up water, so it cooks, right? X-rays. We all know what X-rays are, right? You go to the hospital and get X-rays. You also know X-rays are very powerful. Bad news, you don't want to get too many X-rays, right? Everybody knows that. You'll get cancer, other problems, right? So let's do this little question here. So it's asking, what do they all have in common? They can travel through empty space. Yes, they can, right? You have a cell phone. Your cell phone works. You talk into it. You're talking to your friend, or you send a text. The message goes off. It goes to the local cell tower, and it gets processed by computers. And then your friend receives a message from the cell tower, right? They all travel at the same speed. Yes, all of these things we'll find out. Light is what we can see. Our biological mechanism can see. So we like to think it's special. It is, because we can see these. But all of these electromagnetic waves, we have instruments. Scientists and engineers have developed instruments where we can detect all of those. Just checking the camera, where we can detect all of these waves. We can feel infrared. Infrared is just before light. If you watch spy movies, they were those infrared goggles, right? They can see at night. We can feel that heat. We can't see it. Okay. They all travel at the same speed, the speed of light. They have no mass. Yeah, light waves have no mass, but they have energy, and they do have a wavelength and a frequency. We'll see. By that, if you throw a rock into a pond of water, it'll make little waves, right? Ripple waves. So the waves go up and down, up and down. Sound waves. You're listening to my voice right now, watching this video, And so your computer has a speaker and the sound waves, the waves are coming from your speaker and they're going through the air and they're hitting your eardrum, right? And they move little bones and it goes into your internal ear, and then your brain decodes it all, right? So sound waves. Light though doesn't need air. Light can go through a vacuum, right? So yeah, so all of the above are true, right? They can travel, they travel at the same speed, they have no mass. Okay, these are forms of electromagnetic waves. Well, we've learned about, electrical things, we've learned about magnetism in the last couple of weeks. So this is kind of coming together, right? So we've learned about waves, right? We've heard about magnetic fields, we've heard about electric fields. Well, now there's electromagnetic waves that propagate. Okay, let's keep going. All right, electromagnetic waves. Let me make this one big. We're going to make this one big. So, all right, we'll go this way. Okay, and electromagnetic waves, let me make sure we can see this. Yeah, that's coming in okay. Electromagnetic waves. An electromagnetic wave consists of time-varying electric and magnetic fields in direction perpendicular to each other, as well as to the direction the wave is traveling. What? That sounds hard. Nah, it's not so hard. Okay, so right now, let's just look at this wave here. So just as if you were at a pond with your little brother and you threw a little rock into the pond, it would make a wave, right? This would be the amplitude of the wave. This is the wavelength. So between the waves and the water would be this much. Now your little brother, he wouldn't throw a little rock. He would pick up a big rock and throw it in, make a big splash, right? So the amplitude of those waves would be bigger. So this part, the amplitude would be bigger because your little brother, he can't just throw in a little rock. He's got to throw in a huge one, right? It would be a bigger amplitude. And then if the waves were bigger, if the distance between the peaks and the troughs, so the wave goes through the water, it goes up and down as the waves are coming out from where the rock hit. The distance between each wave, that's called the wavelength. So when I say wavelength, that's what that is. Then the frequency is how many cycles per second, and that's in hertz, named after the scientist Hertz that studied a lot of that phenomenon. So frequency is is the period. How long does it take, right? How many waves in a second? That is the frequency, right? Or the period is how many waves per second. That's in hertz. The wavelength is the distance between consecutive waves. You can measure it peak to peak. You can measure it, trough to trough. You can measure where it crosses the zero line, right? And then, okay? And so this is a wave. Now, unlike a wave in the water or sound waves, electromagnetic waves has this other phenomenon. Because you have a changing electromagnetic wave, or because the electric part changes, well, now we get a magnetic component. We learned this with magnets when we studied motors and stuff in the previous session, right? If your magnetic field is changing, it will induce a current. If you have a current, that will induce a magnetic field. If you just have a charge sitting there, an electron, it'll have an electric field, but it doesn't have magnetism. But if that charge moves, then a magnetic field will form. Well, it's the same for light. So light propagates. So here the light is going this direction. Velocity c is the speed of light, the velocity of light, right? So light is going this way really fast. We'll talk about that. It's going this way. So light has it's a wave, but because it's changing, it's a wave going up and down. There's a magnetic component that goes this way. We don't usually worry about this. you don't talk about this much. The part that we can see, you just hear people talking about, they talk about electromagnetic waves, but they usually concentrate on the electrical portion thereof. But just be aware that light that we see, your cell phones, your radios in your cars, microwave ovens, there's an electrical and a magnetic component to all electromagnetic waves. Cool, huh? And here they're just showing if you have a current, right, going through a wire, right, and here there's a sine wave, so that means that there's an alternating current. We talked about that, right? Your house is all AC, alternating current. So you have a current that changes, and it's going to induce a magnetism in that wire, right? So you folks know all that because we've already learned that, right? Okay. Electric and magnetic fields can be produced by charged particles. An electric field surrounds any charged particle. Magnetic field surrounds moving charged particles, right? So when the electrons are just sitting there, they have an electric field. But if that electric field starts to move, then it'll generate a magnetic field. We've already learned that. So a rapidly alternating electric current in a wire generates magnetic fields whose directions and magnitudes change. Yeah, AC. You know, the wave goes plus, minus, and that's the way the electricity in your house works. You have generating stations, you know, way far away, and they have huge, right, the steam drives these huge electric motors. They spin, and the way the wires are all the distance and the speed at which the generators turn, it generates 60 hertz, AC, alternating current, where it sends electrons, sends them back, but that energy. So although the electrons are going back and forth, the energy propagates down the wires and powers the cities, powers your house, right? Yeah, likewise, a changing magnetic field will produce an electric field, right? That's like if you had the coil and you push the magnet into it while the magnet is moving, it'll generate electricity. The alternators in your car, an alternator in your car, right? It generates a current. Alternator, your car generates an alternating current. Then the way they're configured, it turns it into direct current. But the alternator, the windings have a magnetism, and then as it rotates, because your engine is turning, as it rotates, the battery starts the whole thing. But once the battery starts the engine, then the alternator is what generates the electricity for your car and for the sparks and to run your lights and everything. And the way the windings are, it generates the current, right? The magnetic field generates the current in the wires, and then you have electricity in your car. Okay, and so here's that drawing again. You folks are, okay, I just said all this. I just said all that. Okay, there are many mechanisms to measure the speed of light. The speed of light has been known for a long time. There's all kinds of clever apparatus that experimentalists, physicists, and engineers have come up with over the years to measure the speed of light, including there are mirrors on the surface of the moon. The astronauts put there. So anybody with a laser, and you can point it really well. So that gives some distance, because you shoot the laser. So it has to travel that distance. You got a little bit of time, not much, but so the laser comes, you bounce it off, and then you have a detector back here at Earth. And when the laser returns to your detector, you can measure the speed of light, because you know you flip the switch, you know, it bounces off and it hits your detector. You've measured the speed of light. That's a really good way. Then there's the ways we use on Earth. Use much shorter distances. They have to be very clever, very clever. Engineer. Actually is the ancient word for ingenuity or cleverness. So engineer, people think it's engines. No, it actually means clever. After ingenuity, is it Latin or Greek? I think it's Latin. Anyways, but yeah. So there's all kinds of clever ways to measure the speed of light. It's measured over and over, more and more precise. You know, including mirrors on the moon. So that's pretty cool. The speed of light. This is approximate. 3 times 10 to the 8 meters per second, right? So this is big, right? 10 to the 8 meters per second, right? So the speed of light is very, however, for the size of the universe, the universe is so huge, light actually seems to travel slower. For instance, the closest star to us is the Alpha Centauri system, the closest star system. It takes like 4.2 years. So if you were to shine a laser at our closest star, our neighbor, in the bigness of space, in the largeness of vastness of space, light seems to travel very slow because space is so big. For us, it seems quick because we live in a small little area and bing bang, it goes all over. But for the vastness of space, light actually travels relatively slow, right? When I was young, if you're talking to someone long distance on a telephone, it used to bounce off. They used to use satellites for that signal, and there was actually, you could hear a delay. There was always a click because the phone signal would have to leave Earth, went all the way out to a satellite, bounced off because it would say you're talking to someone in Europe. So you're in America. The phone signal would have to go out to a satellite, bounce, get processed, bounce off, and then go down to Europe. Well, that was far enough. You could actually hear a little bit of a delay. Now, Earth, everything is just cable. They've laid cables, fiber optics along the oceans and stuff, and it's so small that we were not able to detect any kind of a difference. So light, we say it's fast, but it's actually kind of slow once you get to any kind of appreciable distances, right? Okay, this is the important diagram here that I really want everyone to concentrate on, right? Remember that all of these yeah, let me tweak this down a bit. Let me go back a bit. Let me go back a bit. There you go. So you can see everything. Okay. I want you to see everything here. I want you to read all the little. So here what we have is we're talking about, we've named different parts of the spectra. Spectra, yeah, let me explain. So we've all heard of radio. We've all heard of that. We've all heard of AM, FM, amplitude modulated, frequency modulated, TV, right? Back your parents, perhaps they had TVs. They had a TV antenna. Some people still use TV antennas. They just like to be different. There still is TV stations that broadcast over antennas, and there's a lot of people that still like to use them. But it used to be common, not so much anymore. Now they're used cable. We've all heard of microwaves. Right? Microwave ovens. The microwaves were there first. They water absorbs certain microwaves, so they made microwave ovens, right? Microwave oven has there's no flame, there's no heating element. You put the food in, it just magically cooks. How the heck does that happen? Because microwaves go through. And by the way, the microwave ovens the microwaves in your oven, the wavelength is literally, I think, just under 5 inches. It's 4 point something inches or around that much. Pretty cool. So the waves are physically that big, and they're going into your food, and the water absorbs it, right? Different wavelengths get absorbed by different materials. That's normal. Infrared is what we feel is heat. We can't see infrared, but we can feel infrared. We learned in our previous studies that we study temperature and heat. We know that what heat is. The molecules are vibrating. They're vibrating like crazy. They have an internal energy, and that is heat, right? If you have a hot liquid, or if you have an iron bar, it's warm. It's because the molecules are vibrating. Well, those little molecules, they're like little antennas. They're vibrating. They're like little antennas. They're sending out electromagnetic waves. We can't see it, but we can feel it as heat. Eventually, if it gets hot enough, we can see it. So you see, look at this little thing called visible. So we've all heard of radio waves, microwaves, infrared. You can see, like, if you see these spy movies, they have night vision goggles, they can see infrared, we can feel infrared. There's this tiny little portion we can see, ultraviolet. We can't see ultraviolet, but this is what, when people like me, very fair skin, if I go out in the California sun in the summertime, I gotta put some kind of sunscreen on, right? And it'll always say UV, broad spectrum, right? That's ultraviolet. On the sunscreen, it'll say UV. What they mean is UV is ultraviolet, beyond purple. Because visible light that we can see is red. The colors of the rainbow go from red, orange, yellow, green, blue, then there's this color indigo that they made up. and then violet, right? So we can only see those colors and combinations thereof. We can't see infrared. Deer and possums and stuff, and night animals, they can see into the infrared a little bit. Birds can see into the ultraviolet a little bit. When birds see other birds, they're like glowing. Sometimes when you look at birds' feathers, they seem like they're a phosphorescence kind of a thing. Well, birds see other birds like, wow, they can see them far away, like they're like these bright. So that's why birds can react to each other. They see each other from far away, really bright. Then you get into X-rays, right? X-rays are powerful. If you're going to get an X-ray, you just want a quick X-ray at the dentist. You don't want to get a lot of exposure, right? The dental people, when they take your X-rays, they'll wear like a lead apron to protect them from repeated exposures. So, right, very high energy gamma rays. So here's the way it works. Wavelength. Notice this is 10 to the 6 meters. That's big. Here's 1 meter. Well, we all know how big a meter is. A meter, I can't show it here, but a meter is about this is big, right? It's a little bit bigger than a yard. A yard is 3 feet, right? So this is about a foot. 3 of those is a yard, and a meter is a little bit longer than a yard, right? So Felix, you're telling me that TV signals are about this long? Yeah, that's exactly what I'm telling you. And here, notice that the waves get shorter. So here you have waves that are about a meter. Here you have waves 10 to the 3, 10 to the 6. Remember, 10 to the 2 would be 100 meters. Yeah. So that's why like your radio antenna on your car is big, because there's a bit, like my car has a radio antenna. It's about this big. I don't know, maybe 2 feet, because it has to be big enough to get the waves, right? And the way it works is that the wave comes through, it moves the electrons in the metal antenna up and down, and then that signal goes down where it's amplified, and then signal processing. That's the way it works. Likewise, to send an electronic signal, you move the electrons up and down with the signal. Those electrons going up and down, they propagate the electromagnetic wave outwards. That's how you send a signal. That's how your phone sends a signal out. Now your phone works in a different frequency wave, not here. We need a bigger antenna. The engineers, of course, old-fashioned phones had a bit of an antenna, right? The analog ones. That's why they went to digital. They can use a small antenna. Your phone is small, right? But notice here, so these waves here are much bigger. They go from 10 to the 6 meters, 10 to the 3, 1,000 meters, 100 meters, 1 meter. They get really small, 10 to the minus 3, 10 to the minus 6. Indivisible, you can fit 200 wavelengths in the width of a sheet of paper, right? The pupils in your eyes are really small. So what you can see, the visible wavelength, you can fit 200 waves. Are you able to see this? Oh, you can't see it. So here's the book, right? The width of a sheet of paper. How thin a sheet of paper is, right? See how thin it is? You can fit 200 waves in the width of a sheet of paper, so it gets really small. But you notice that X-rays have a lot more, everyone knows X-rays have a lot more energy than, say, microwaves or radio waves, right? If you were to turn a radio on in your house right now, you know that you would be able to pick up radio stations. So the waves, they're not killing you, right? If you were right next to the antenna, they would. But X-rays, you know that those are dangerous. So what happens is, the wavelength is smaller, but there's more energy. So that's what I want you to know. So the wavelengths get smaller, but as they get smaller, there's way more energy. Gamma rays are nasty rays. These are nasty things. Thankfully, our atmosphere filters out most of those things. Gamma rays are really nasty, right? They happen when there's nuclear explosions. The sun emits gamma rays. When there's space has a lot of gamma rays because stars are supernova, or in the sun, the sun is a thermoelectric thermonuclear fusion is what powers the sun, right? Where hydrogen is fused into helium, and then gamma rays come out, right? And so gamma rays happen from nucleic processes. So I want you to know this. So here the radio waves are longer, they get shorter as you move to the left, but the energy here on the left is higher and it gets weaker as you move to the right. You've all heard these terms before. All I'm doing is organizing it for you. You've all heard of radio waves, microwaves, infrared, ultraviolet. We can see this little portion here, our biological mechanism, our electromagnetic detectors in our heads that we call eyes, right? What happens is that a wave comes. It goes through our lens in our eye. It goes back. It hits the rods and cones. There's enough energy in that wave that it reacts with a protein, causes a chemical reaction. Your brain processes it, and that's called seeing. Pretty cool. So, by the way, where is color? Right? We're talking about color, like red, orange, yellow. And I said now that light is an electromagnetic wave that has an energy, a very specific energy, a very specific wavelength. So where's the color then? When you look at a tree, are the leaves of the tree green? Well, it's reflecting at a certain wavelength, and it has a certain energy, and it causes a certain chemical reaction in your head. But where's the actual color, the hue? It's only in your head. Color does not exist without life. Say all life died on planet Earth and there wasn't any life, there's no color. Color is only something that exists in your brain. The rays themselves don't have the color. Isaac Newton realized this hundreds of years ago, right? So it's just the way that our brains do signal processing, right? You have to be able to see deer in the green forest and hunt them. So because we evolved as hunters and gatherers, right? So color is only in your head. So when people say something like, "One thing I know is the sky is blue," you got to go, "Oh, sorry, dude, you don't even know that." The blue is in your head, right? So now the waves are coming down at that specific wavelength, and they have a specific energy that causes a specific chemical reaction in your head. But the blue, the hue that you're seeing, that's only in your head. So you want to know this. This is very important, okay? I want you to know. And the good news is we've heard of all of these. You just probably haven't had it organized before. So the wavelengths here are very long, right? That's why some antennas are really big. Radio stations that used to broadcast in AM, they were these incredibly high things because they have to send these much bigger. TV antennas were big. People had on top of their roofs, right? And then so they needed that to accommodate the bigger waves, right? And then microwaves, right? Yeah, microwaves, they happen to heat up water, right? Ultraviolet, you've heard of the ozone layer? The ozone layer is what the ozone is up in our atmosphere absorbs ultraviolet light. Ultraviolet light is dangerous. If we didn't have the ozone layer, it would kill life on Earth. Because this is what burns my skin, right? And this is only because a little bit gets through. If there was no ozone layer, all that ultraviolet would come through and it would just kill all life on planet Earth. So it's very important that we have that. And then of course, different substances like carbon dioxide and methane and such, they absorb in the infrared, right? You've heard of the greenhouse effect. Right, so those absorb in the infrared, and that's why, yeah, if you introduce more carbon dioxide, methane into the atmosphere, it's going to absorb more infrared, and our atmosphere gets hotter. It's just basic physics and chemistry, right? These nutbags that say that humans are not inducing global warming, well, they need to take my class. They need to take some science classes, right? Okay, and then yeah, different types of waves can go through different types of material, right? Let's talk about that. I think it's going to be coming up. Electromagnetic spectrum. We got our. Okay, and then here's a little. I'm not going to bother doing problems. I'm going to show you a problem though. So the speed of light, velocity. The symbol is c. That's the speed of light. If you take the frequency at a specific, and you multiply it by the wavelength. So if you were to take a specific hertz, right, a specific frequency, and you multiply it by the wavelength, you're always going to get the speed of light. So that's the way it works, right? As you go this way, as you go this way, the frequency increases, but the wavelength decreases, and you multiply them together, it always equals the speed of light, right? So that's the way that works. So that's the speed of light. So that's pretty cool. This equation you have to know. We'll look at some problems in just a bit, okay? Okay, so here's a little, what we're going to do one right now. So if your wavelength is 10 meters, down here is wavelength. So here they're saying 10 meters. So here's 1 meter, here's 1,000 meters. 10 meters would be here someplace, right? The speed of light in a vacuum is a constant. It's always this, right? Then so if you know what your wavelength is, you always know what the speed of light is. It's always the same. What is the frequency? Well, the frequency is simply, so here's frequency, so you would take the velocity, the speed of light, divided by lambda, which is the wavelength. So frequency is equal, because you're given the speed of light. You know what the speed of light is. You know what the wavelength is. So it's just the speed of light divided by 10 meters. Your frequency is 3 times 10 to the 7 hertz. Okay? Simple as that, right? You have to know that. And then here's just one more. So if you're using, so what is the frequency of light waves with a wavelength of 6 times 10 to the minus 7? So that's here someplace. Here's 10 to the minus 6. Oh, I'm sorry. Yeah, if your wavelength 6 times 10 to the minus 7. So that would be here someplace. So the speed of light again, you know, velocity is equal to the speed of light. That's a constant, right? And it's just equal to your frequency times your wavelength. So your frequency would be equal to the speed of light, which you know. You've been given the wavelength, and in the simple division, you're going to get 5 times 10 to the 14 hertz, right? So your frequencies get really high going this way, but the wavelengths get really small, and vice versa going that way. Okay? Yeah, so yeah, radio waves X-rays come from, you know, energy of atomic electrons, right? Gamma rays come from the inside of an atomic nucleus, right? Gamma rays the sun produces gamma rays because there's thermonuclear fusion. Radio waves, we make those all the time. We accelerate charge in an oscillating electric circuit, right? So you accelerate, you have the signal going in an antenna, the electrons are going up and down, that generates radio waves, and you send the radio signals out, TV signals out, right? Yeah. And then X-rays, they have machines where you can take X-rays of people, right? Energy transitions of atomic electrons, right? So that's down at that level. That's not putting them through a big antenna like you would for radio waves. Then gamma rays are produced, you know, the military, I'm sure, has gamma rays weapons and stuff, but you know, that's produced by nuclear reactions, right? But let's talk about. Oh, let me go back to that one. Where am I? No, I'm here. Okay, yeah, this is important here. What goes through what? Okay, and what materials would they go through? Well, we know that X-rays pass through a lot of material.